Good morning, grade 10s. Welcome to our new time slot. Sure, I'm glad to see that I've got most of you guys here. I was slightly worried that a lot of you were not going to join me. Guys, Braden put here and he says he can't find the video for the 7th of April. So, Braden, thank you very much for telling me that. I will go and follow that up. We're actually at the moment in the admin side busy with a huge recon of all the videos that are on YouTube and that are not on YouTube. So if you guys pick up videos that are not on YouTube, please just pop them through to me like that and I will sort them out. Let me quickly do the reset mic thing. We all know. Come on. Let's see if that is better. Hello, Tyrese. Hello, guys. Okay, so Arthur said he was unable to join all of last week. So Arthur, all of last week, we looked at electrical circuits. Okay, so we started with the idea of, remember with electrostatics, we have a electron or a electric charge moving from one object to another if we touch them. With electrical circuits, we now have wires with electrons in them and we give those electrons energy and we make them move. Okay. Dum, dum, dum. Miss P, you woke up early. Hi, Nelly. Hey, Kamal. All right, guys, so it looks like YouTube is behaving itself. Let's hope. Okay. All right, guys, so last week we looked at series circuits and parallel circuits, and we looked at them separately. So I'm just going to go back and just touch base back on them. And then we are going to start combining them. Okay. So don't panic. Like I say to you guys, we will do this the whole week if we have to. Okay. It is very important to me that you guys can really master this stuff. Okay. Right. AFK what, dude? Okay, so today we are going to look at combined circuits. So let's just touch base and think about series circuits and then parallel circuits. So in a series circuit, electrons only have one possible path. Okay? So the basic rules are the current is the same everywhere. Because remember, current equals flow of electrons, charge per time unit. The potential difference is split because each component uses part of the energy given by the battery. So the sum of the potential differences of each of those components is equal to the total differences. Oh, sorry, Tyrese. I get it. Okay, so we drew a little circuit like that. You guys all panicked because there were so many components in, but I just use it so that you guys can see the math. So the current there is equal to the current there is equal to the current there. Okay. If I take that potential difference plus that potential difference plus that potential difference, it gives me the terminal potential difference. So the total energy given to the current, to the circuit, is a better way of putting it, by the cells. More than one cell, we call a battery. Right, and then we said that total resistance in a series circuit, very, very easy. We just whack them all together. Okay. Cool. So now in parallel, we give electrons a choice. So the current splits. Okay, we spent a lot of time on that on Friday, and I know that's a tricky conversation. Okay, and the potential difference in each branch ends up being the same as the terminal potential difference. Okay, so calculating resistance when we work with parallel circuits is just weird, and we saw that. Okay, so if I give you a thing like this with 3 branches, don't panic, we did this. I can say that the current through the top branch plus the current through the middle branch plus the current through the bottom branch is equal to that total current there. Okay? And because I've got only this parallel component, the energy used here is equal to the energy used there in the middle branch is equal to the energy used in the bottom branch, and they are all equal to the energy that the cell can give. Okay, and you guys all know my drawing skills, they kind of fly out the window, so yeah, sorry. Okay, and then we said that the total resistance, we've got this weird equation, and I said to you guys, I strongly recommend that you don't write it as 1 over R, okay, that you put this whole thing in a bracket and then you make it minus 1. Okay, so these are the ideas for parallel and series separately. Zelna, yes, I will gladly admit that my drawings are unique and special. Okay, I can deal with it. Okay. So, guys, there's many ways in which we can combine series and parallel circuits. Okay, many ways. Today, I'm going to focus on one way, and then tomorrow I'll show you a different way. If we don't quite get comfortable with today's way, then tomorrow we do it again. Okay, guys, there really is no rush. The stuff is important. Okay, and I'm quite willing to spend quite a bit of time on it. So, let's work. Oh my goodness. Let's try this. No, too much. Sorry guys, I'm like moving my little tablet around, seeing if I can get a straightish line. There we go. Okay. And let's attempt to use the ruler, because then at least it's a relatively straight line. There we go. There we go. No such thing as straight lines. No, I heard somewhere that the only people that can draw absolutely straight lines are people that are psychopathic. So like that have no feelings. They can draw straight lines and round circles. I don't know what the theory would be behind that. Okay, so don't chuck that my way. Okay. But yeah, like I said, I don't know how much truth there is in that. I'm definitely not one of those. Okay. So guys, in those 2 gaps there, I'm going to put ammeters. Okay. Now I'm going to use this entire bottom bit. Oh my goodness. There we go. I'm going to use this entire bottom bit so that we can draw resistors in it. Okay. So we are going to have a resistor in series, and then we're going to have 2 in parallel. Okay. So just stay with me. I'm going to attempt to kind of finish up these lines. So we're going to have a resistor in series. So let's call it 2 ohm. Okay. Like I say here, I'm going to put an ammeter in. And here I'm also going to put an ammeter in. I don't know what that number is going to be. It's going to leave it out for now. Okay. So now I am going to have 2 resistors like that. Okay. So guys, this is the basic idea. Okay. Basic idea is that we have a resistor in series to 2 resistors in parallel. So this part here is parallel and the rest of it is in series. Okay. Right. So before we do too much, let me just tell you that we have these 3 cells give us a total of 2,5 volts of energy. Okay. So the first thing we are going to do is I want us to calculate the resistance of this bit here. The way that they word it is they say calculate the effective resistance in parallel. Okay, so the first thing we're going to do is we're going to calculate the effective resistance. Of course it would be on the wrong place in the page. It's fine, I'll just move around again. Effective try that again. Resistance of the 3 ohm and 5 ohm in parallel. Okay, guys. So that is the first thing we're going to do. Okay? Calculate effective resistance in parallel. Again, on your information page, you are going to get this formula. Oh. Okay, it looks something like that. I can't exactly remember what it is. I don't have one in front of me now. Okay, I strongly recommend that you don't write it like that, that you remember that this 1 over, I can write like this. With that -1 there. Okay, it makes it a lot less scary and it makes the calculations a lot easier. Okay, good job, Tarish, if you remembered about my -1. Okay, so this is now going to be into this formula. I'm going to choose that one as R1 and that one as R2. Okay, so I'm going to say 1 over 3 plus 1 over 5 to the power -1. Anyone got an answer? Corley, I think you mistyped. Yeah, no, I thought so. Good job, Ash. Good, good, good. Yes, so we're going to round to 2 decimals, okay? But you can leave it 3. I'm quite happy for you guys to leave it like that, okay? But if you want to, you are more than welcome to round to 1,88 ohms. Okay, well done, guys. Well done. Well done. It's still there. It's still there. Okay. Now, just whoa and just stay with me. Okay. I want you to imagine that we now take this 3 and 5 ohm, this entire parallel bit, and we cut it out. And I tell you to replace it with one resistor that has the same effect. Can you guys see that that is going to be one resistor of 1,88 ohms or 1,875 ohms? If I want to, let's use a funny color. If I want to cut this whole thing out here, and I want to replace it with one resistor, I'm going to replace it with one resistor in series that has a resistance of 1,875 or 1,88 ohms. Okay. So now normally the next question up is calculate the total resistance of the circuit. Okay. So the next question up is going to be calculate the total resistance. Ooh. Resistance. Okay. So now let's think about it. Okay. I have calculated this parallel bit is equivalent, the same as one resistor of 1,875 ohms. Okay. So if I redrew that bit there, I could redraw it like this here at the bottom. I'd have my 2 ohm there. And then instead of having this whole weird parallel bit, I would have one resistor of 1,88 ohm. Can you guys see that? That is the crux of this matter. That's kind of like where it gets a bit tricky and hard and weird. Okay. So now I have this, and these two are in series. Can you see? I've taken this parallel component and said, well, I've just calculated that it's exactly the same as 1,88. And I still have this 2 ohm here that's in series to this thing. So does anyone want to take a quick stab, a quick guess? You don't have to show me the formula. I'll write down the formula. Corley, Marie, Ashley, yes. Tino, yes. See? It's not that hard. Not that hard. Good job, good job, good job. Oh, you guys make me proud. So now I can say, and like I say, I'm not expecting you guys to write this down, okay? So I would have written it like this. I would have said, well, I'm going to make that thing there R3, and this whole thing here is going to be equal to RP. So the total resistance is going to be 2 plus 1,88, which is equal to 3,88 ohm. Now, guys, if you kept that, and like Ashley showed, if you had kept that in 3 decimals, okay, you can write that in 3 decimals too. Remember, the instructions is at least 2 decimals. So that means that you can keep answers to more than 2 decimals. Okay. All right, guys. So now we have the total resistance. If I look at the picture, the big picture, okay, I'm just going to add what we've just calculated up here. Okay, so we said that this whole block here is equal to 1,88 ohms. And then we said that the total resistance is equal to 3,88 ohms. Okay. This voltmeter reading here, the potential difference across the battery, so the terminal potential difference because the circuit is closed. This potential difference here, guys, remember we can say that it is the terminal potential difference, which is equal to the total energy available to the whole circuit. Okay. So, does anyone want to tell me what we can quickly calculate without too much effort if we know total potential and total resistance? I'll give you a hint. It's in the triangle, which I clearly can't draw today. What things on the whiteboard, Corley, do I need to let me just reshare it. Is that a bit better, Corley? Does it pick back up again? I don't want to make it too small because then you guys, and you guys can't see what's going on. Okay. Guys, let me just erase that horrific triangle. Oh my goodness, that is like the worst one ever. Oh, it takes a couple of seconds. Yeah, Corley, I'm actually today when I'm done teaching you guys, Kamo needs me to redo series. Kamo, I can redo. Kamo, do you mean redo the series of this example, or do you need me to redo series in total? Yeah, Corley, it does take a while to do it up, but I also think that somewhere between my laptop and the cloud where the whiteboard is stored, there's a bit of an issue. So I'm actually going to see if I can't get a whiteboard that doesn't speak to the cloud and then back, that's just on my laptop. But I'm going to do that today after I've seen you guys. I might actually try Mimeo. Okay, Kamal wants me to redo question 2. Okay, so Kamal, you are quite comfortable with me getting to parallel. Okay, that's like, okay, I take that block there, and then I can calculate the parallel. Now, Kamal, once we've calculated this resistance here, what we can effectively do, and I know this feels very weird, is, come on, we can say these two resistors here, the 3 and the 5, I've calculated is the same size as one resistor that has a size of 1,88 ohm. And so to make my life easier, because remember last week, we only looked at series circuits and we only looked at parallel circuits, okay? Those are like the core things that we have to use. So now we have to think outside the box. We have to think, how can we use the resistance we calculated here and add this 2 ohm to it. Okay, because yes, last week we didn't look at that at all. Like we only looked at, I have resistors in series, one next to each other, or I have resistors in parallel, one on top of the other. I didn't look at something like this. So what we are now saying is that if I now have this resistance here, so I know that the 3 and the 5 ohm has the same effect as one resistor of size 1,875 or 1,88, then instead of having this entire parallel bit here, I can view it, I can look at it as one resistor with 1,88 ohms. Okay, so can you see I took these two here and I replaced them with one that has the same effect as these two guys here. And now I know this is much smaller than both of those. That's normal. Parallel components always have a lower resistance than the resistance inside of it. That's fine. Okay. Yes, Braden, I'm quite happy for you guys to calculate the current because I know if Kamal gets this, the current's going to be easy. Okay. So you guys have total volts, 2,5. So you've got volt VT equals 2,5 volts and RT equals 3,88. I can't draw an ohm sign. Okay, so Kamal, I take this parallel bit and I replace it. And now I have two resistors in series. Okay, and now I use the resistors in series and I say, I make this one resistor number 3. And this whole bit is the parallel component. That's why I write RP here. And then it's quite simple and I just add them. I think the problem comes in is this idea that I've now taken out the parallel component completely and replaced it with its equivalent. Okay, this is a trick I learned how to use when things get more complicated, is I actually just redraw them. Okay, does that help, Kamal? Okay. All right, I'm glad that helps. All right, guys, so we are busy calculating. What is that doing down there? That's like math lit. Oh my goodness. Whoopsies. All right. We are now calculating. Boom, boom, boom. We are calculating the total current. And you guys like your triangle. So I will show you your triangle too. And I will remind you that you do get this formula. Okay. And that we know that the total resistance is, no, not 3,88. And we know that the potential difference over is 2,5 volts. You can either use this one. Remember, you want to calculate I. So it's going to be V over R. Okay. Or you can use this formula here. It is completely up to you. Because this becomes very easy, I'm just going to show you this one. I apologize if anyone gets bored. But it's simply so that those of you who like to use formulas exactly from the information page, like this nerd here, like me. Okay, I'm not pointing at you, I'm pointing at me. that this nerd here, I like to write down stuff exactly from the information page. Okay, right. So now I need to manipulate this thing. You guys know me. I flippin' hate fractions. So I get rid of the fraction. Okay. What I do on the one side, I do on the other. You guys never thought you'd ever use that ever again, didn't you? Ha ha ha. Here it is. Okay, so I get 3,88i equals 2,5, because remember that and that cancelled out. Then I want I on its own. So I want to get rid of 3,88. What I do on the one side, I do on the other. So that and that cancels. Okay. So the total current equals divide by 3,88, calculator, 2,5 divided by 3,88, or 0,6443, blah, 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 blah. So I'm going to round that to 0,64 ampere. Okay. Guys, it looks like you got it. Nice. Happiness is. Okay, very, very, very happy with that. Well done. Yes, you can. Ashley, you can just use the flip and triangle, okay? I just did this bit here. because that is the formula you get on the information page. Okay. Tyrese, are you talking about the mathlet here on the side? I'll take Corley away, don't worry. There we go. I don't mind seeing you guys. I really don't. Like, you guys I trust. It's the non-people that shouldn't be in our class. Okay, right. I am going to go back up to the diagram. Okay. It's okay, Corley. Don't panic. Don't panic. All right, so I'm going to go back up to the diagram, and I'm actually going to add this information in here. Okay. Right. Bring, bring. Oh, dear goodness. I do think... No, you guys are not nice. You are awesome. Like, I can't use nice to describe you guys. I can't. It's not a fair description. You guys are absolutely amazing. Like, I wish I had words, guys. I really wish I had words to describe how much I enjoy teaching you and how you've made lockdown bearable. Okay? I really enjoy teaching you guys. You don't even have to for a second think that you are, I don't know, average. I don't know which words you want to choose to describe yourselves, but unless they are awesome, then I will not accept them. Okay, I'm redrawing this because it got a bit much. Okay. And I know you guys, like, your brains are limited when my drawings become absolutely, completely crazy haywire. Okay. But now, of course, I didn't use a ruler, so it looks worse. Okay. You are more than nice. You are extraordinary. Oh, thanks, Tyrese. And you know what? I think for me, okay. Oh, thanks, Miss B. I think for me, it's important to give you guys the energy you give me. You know, there's no point in you guys being like on it and with me and working, and I'm sitting here and I sound like this, and you know, I tell you that it's not gonna work. Okay, so guys, like Miss P the one day who nailed me said, man, sure, you're like very tired today and I'm very worried about you. I appreciate that. Okay, I really, really do. If I'm not giving you guys, yeah, I know. If I'm not giving you guys my 100%, you are allowed to nail me. That is part of your job. Okay, you are allowed to say, sure, ma'am, are you sure? Okay, you are allowed to. Okay, so now we have all of this information. Okay, now there are a lot of things that we can calculate from here. But what I want you to calculate is this voltmeter reading over the 2 ohm resistor. I'm going to say it again. I want you to calculate the voltmeter reading over the 2 ohm resistor. So just take a moment, just think about it. Okay. What do we know about series potential differences? You only have to give me one word. Do they remain the same? Do they split? Series potential differences. Okay, Tyrese, I get where you're going. Apocalypse Bird. Okay, Zalne. Guys, remember that the electron, let me just move it down a little bit. The electron starts here with 2,5 volts of energy. This ammeter doesn't take energy, but this 2 ohm takes some energy. So now the electron has lost some of the 2,5 volts energy. Now it gets here and it can either go up or it can go down. And there's nothing after it. So whatever energy is left over after it's given that will go there. Okay, so potential difference in series split. Got it? Potential difference in series split. Okay, now Ash has given us a number. Guys, we know what the resistance is and we know what the current is through that. Okay, so we've got R is equal to 2 ohm. R is equal to 2 ohm. And the current through the 2 ohm resistor is 0,64 ampere. So, seeing you guys don't like me doing maths and I don't like doing maths, we want V, so we can say V equals IR. Sure, that's the easiest maths we're going to do all day. So it's equal to 0,64 times 2, which is 1,28 volts. Hey, easy peasy lemon squeezy. So now I'm actually going to take that V1 out and I'm going to replace it with that 1,25. Oh, 1,28. Okay. Question. If I've now used 1,28 volts, how much volts, how much is left for the parallel bit? Reminder, I started with 2,5. So if I've taken 2,5 and I've used 1,28, that means that if I put a voltmeter across any part here, I have 1,22 volts left for that thing there, right? And remember, we said that the volts stay the same. So that one there is going to be 1,22 volts. And that one there is going to be 1,22 volts. And now we can work out current. You guys see how you just have to, when you have a circuit like this, you chew away at it a little bit at a time. Okay, guys, we've got like 5 minutes left. Can I give you a homework problem? Yes, no? It's going to look exactly the same, just different values. Okay. So I'm giving you 2 cells, and the 2 cells have a PD of 6. And then I am giving you a parallel component. And the parallel guys have got at the top a 3 ohm, a 2 ohm at the top and a 3 ohm at the bottom. And in series to that, I have a 6 ohm. Okay, the questions are exactly the same as this one. The first thing I want is the parallel resistance. The second thing I want is the total resistance. Then I want the total current. I like that. All answers always stay breezy. Okay. And then after you've worked out all of that, you can work out that voltmeter. You can work out that voltmeter there. And then let's pick a random one. Let's go for the current through the 2 ohm resistor. Okay, so it's going to be, I want you to calculate V1. Then you're going to calculate V2, which is the resistance over parallel. And then I want you, which we didn't do today, to see if you can calculate the current that goes through this 2 ohm resistor here. All right, guys, big enough so that you can see? I know you've got this. I know you do. And what I'll do is I will redraw this very nicely and neatly, okay? And then I will try and like, maybe I'll try and PowerPoint the steps, okay? And then tomorrow we'll look, you guys, RP is the parallel resistance. So Carolina, for the parallel resistance, you're looking here at this branched thing. Okay, guys, Lada, if you just popped in here, then where were you? Okay, guys, I know you've got this. I know you got this. Yes, Miss P, he's slightly late. You might have to share your notes. Okay, guys, tomorrow, 10 o'clock, we will start with this problem, okay? And then, if you guys tell me, ma'am, this is okay, then I will show you a different way in which we combine series and parallel, okay? If you tell me tomorrow, sure, ma'am, please do this again, then we do another one like this, okay? Right, guys, I've got you. You've got this. And you are flippin' awesome. Have a gorgeous day. Yeah, ooh, Have a gorgeous day, guys. Stay safe. And I'll see you guys again tomorrow. Bye, guys. Be good.